Bismillahirrahmanirrahim. This section deals with computational aspects of the CCR model. You can skip this section, but I only review the contents. First, there is a computational procedure for the CCR model. Note that the CCR model in envelopment form has two phases. The first one minimize theta subject to the constraints, and in the second phase the summation of the slags are maximized subject to the constraints when the fixed value for theta, the optimal objective function value of the first phase, is put instead of theta in the constraints, but the other constraints are the same. Note that this is a linear programming. Both in the first and the second phase, you indeed solve a linear programming model. So you can solve it by any LP solver. Also, there are some special solvers that you can use for solving this model. By using the usual LP notation, we can rewrite this model as you can see here, that the data and the variables are defined here. In the first phase, an LP is solved, and here it is explained how to solve this two-phase model computationally, and it with less computation. Here about data envelopment analysis and the data, some contents are reviewed. How and where is the name of envelopment from, and how we can determine the weights. Indeed, it corresponds to the optimal values of the multiplier from solving the envelopment form. However, there are some reasons here that solving CCR model using the envelopment form is preferred. The first reason is the computational effort of LP is more dependent on the number of the constraints. In DA, usually the number of DMUs n is considerably larger than the summation of inputs and outputs. So you know LPO has n constraints, indeed n plus 1 constraints, but DLPO has n plus s constraints. So we prefer less constraints. That means DLPO for solving the CCR model. In addition, the memory size needed for keeping the basis or its inverse is a square of the number of constraint. So because n plus s is usually much less than n, so this matrix is smaller, the basic matrix, because of the number of inputs and outputs. The second reason is that we need max slack solution, and this solution can be obtained by solving the envelopment form. The second one is the interpretations of DLPO are more straightforward because the solutions are characterized by as inputs and outputs that correspond to the original data. Now we consider an example with 7 DMUs, each have 2 inputs and 1 output. The data you can see from this table. For example, A uses 4 of first and 3 of the second input to produce 1 output. B uses 7 of the first and 3 of the second input to produce 1 output. You can see from here that A performs better than B, but we can compare all of these and determine the efficiencies, the reference set, and indeed solve the CCR model for these DMUs. So since we have 7 DMUs, we need to solve 7 linear programming in 2-phase linear programming model. That means 14 linear programming model indeed. For A, we have these 2-phase linear programming model. Note that only we put the data on the CCR model. The first objective is minimizing data. The second one is indeed maximizing the summation of the slacks or minimizing their minus. For A, 4, 3 are for theta, and these the other input and output values and the outputs are used to write the constraints. Note that the variables R are non-negative, but theta is unrestricted. Also we can see, of course, that theta is always strictly positive and its optimal value is less than or equal to 1, and it's strictly positive. We will see that this model can be solved graphically later, but here the DA solver sample CCR1 source is used to solve this model. For A, the optimal objective function value is less than 1, so it is obvious that this DMU is not efficient. And by using the optimal solution, it is seen that the reference set for A is D and E, since only these lambdas are not zero. The max slices are also zero. Note that the values of lambda shows also the proportion of, for example, here you can see that lambda d is much bigger than lambda star e, so the proportions contributed by d and e to the point used to evaluate r shows that d is more similar to A, and indeed to determine the efficiency, this is much more important than E. As we defined before, the projection can be determined as you can see from here. Indeed, by using the optimal solution, that is theta star of the inputs of A, can be determined by this multiplied by input of D. This is lambda star D, and lambda star E multiplied by input of E, and the output of A is also obtained by these optimal values. Note that the other DMUs, their proportions are zero. So the projection can be obtained as you can see here. Indeed, the first input of the DMU can be this, and the second one this. That is about 40% reduction on the inputs, and the outputs of course are not changed because the slags are zero. Not that you don't see any slag here because the value of optimal slags all are in max slag 0. You know that by solving a model you can determine also its optimal solution of dual. So the solver also finds the optimal values of the dual, as you can see from here. Now consider DMU B. So we only put the data of DMU B here as the multiplier of theta. So we would have the same model, but instead of 4 theta in the first and 3 theta in the second constraint, we would have 7 theta in the first and 3 theta in the second constraint. All the others are the same. This is also a two-phase linear programming model and can be solved by the LP solver, but here it is solved by a special solver of the CCR, the worksheet sample CCR1. As you can see, the optimal values are obtained. Here, the max-like solution, the optimal solution of the dual multiplier form, and the envelopment form. So we have this same for B. Here also B is not efficient. The slices, max slices are 0. C and D are used to determine the efficiency of B. Indeed, B is compared with C and D, and this comparison D is more important because lambda star D is bigger than lambda star C. The reference set is C and D. Since only these lambdas are strictly positive. And similarly, we can find the projection, the CCR projection for B, as you can see from here, and this shows how we can reduce the inputs or increase the outputs. Here, of course, the outputs, there is no change in the output, but the inputs can be reduced about 37% reduction. If we solve the model for C, D, and E, these are efficient. It means the theta star value in the first phase is 1, and the lambda and the summation, the S-likes, max S-likes value also would be 0. For E, this is the optimal solution of the envelope and the weighted model. You see theta star is 1, but we have S-like for the first input. This shows F is weak, efficient. Here, by using the max S-like solution, and because only C has lambda star C bigger than 0, so the reference set is C, a set that contains only C. And changing the inputs and outputs to make the DMU indeed F efficient is shows here. Here again for DMUG, you can change the LP model by, as you see, changing the multiplier of theta only, and by solving the model, the values, the optimal values are obtained, as you can see here. The reference set is a set with one component E, and changing the inputs and outputs are shown here, and this is how we can determine the CCR projection, as you see. Note that the optimal solutions for the CCR model was obtained by a CCR solver. However, by seeing this figure, indeed as we will show later, and of course as we saw before, you can solve the model also graphically. For example, by using the DMUs, you can make easily the production possibility set. Note that by the assumptions, you can see that this is the production possibility set, and by using this, as you see, E, D, and C, for these DMUs we cannot indeed determine DMUs with less inputs in the production possibility set. So E, D, and C are efficient. For F, you can see we cannot determine DM point in production possibility set that both of its inputs is less than F. Indeed, radially that shows the value of by the value of theta star. The theta star is 1 because we cannot reduce simultaneously the inputs of F, but we can reduce the first input of F. Indeed, if you compare C with F, you can see that C, the first input of C is 2, indeed smaller than the first input of F, but the second input of these two are 1. This shows the theta star for F is 1, but the slack of the first input is 1 minus is 2 and is not 0. The max slack, of course. The slack can be, you can also put lambda F equal to 1, theta is 1 with slack 0, but the max slack, when you determine, you solve the second phase, the max slack is the correspond to the solution that lambda C is 1 and the other lambdas are 0 and S minus 1 would be 2. For G, as you can see, if we reduce both inputs, we can find this point named R. R has less inputs comparing with G in both inputs indeed, and their inputs are reduced simultaneously but by the same ratio. However, R comparing with E has the same first input, but its second input of E is smaller than R. So to determine efficiency of G, the reference set is E. This means lambda E, the optimal value of lambda E is 1, and by putting lambda E 1 and the other lambdas 0, you can determine easily the value of theta star. That is the from or if the same as if we divide the distance of the origin to R to the distance of origin to the G. For A, as you can see, we can reduce by the same ratio first the inputs to reach Q. But Q itself is between E and D, so it is convex combination of D and E. Here also you see to determine the efficiency of A, we use only D and E. So in the model, you can put all the lambda equal to 0, but lambda E and lambda D are determined when you put the other lambdas equal to 0. The constraints only have three variables. One is lambda E, another lambda D, and the other is theta. And indeed, as we will see later, and of course we saw before, theta star and the lambdas optimal values can be obtained by solving three equality constraints with three variables that can be solved easily. Of course, I will give another example and I will show it in that example. For B, if you reduce the inputs, you will reach to a point between D and C. So for B, the reference set is D and C. You can determine the optimal objective value graphically without using any solver, also by putting all the lambdas equal to 0 but lambda D and lambda C. Then you will give a equality system with three variable and three equality constraints that you can solve it, but easily to find the optimal solution of the CCR model. In this table, the results are summarized for all the DMUs. As you can see, the CCR efficiency theta star, the reference set, the S-lags of inputs and outputs with the excess and shortfalls.